we're going to look at acid and base reactions. Okay, and that's kind of what you looked at on your homework on those couple problems, the total reactions that happen between acids and bases. And we're going to focus on Bronsted-Lowry reactions. Okay, which means what are we focused on? Are we focused on electrons or protons? We're focusing on the trading of protons, or H+, okay, hydrogen ions. Okay, so what we're going to be looking at here is we're going to study the proton transfer taking place in an acid-base reaction. Okay, so that's what Bronsted-Lowry's focus is the proton transfer, but that's what we're going to look at in our acid and base reactions. Okay, so we're going to get two new kind of vocab words in terms of acids and bases.
So we're having a test over this, but it's not going to be on the final?
All right. So our new terms that we're going to look at is something called a conjugate acid and conjugate base. And I'll start with the conjugate base. Okay, a conjugate acid and a conjugate base. So a conjugate base is the compound, or your book calls it a species, the compound that remains probably. The compound that remains after a Bronsted-Lowry, I'm going to initiate it like that, acid, has given up a proton. Right, and that's how I abbreviate proton, because we know protons are really trading of hydrogen ions. Okay. So a conjugate base is the compound or the species that remains after a Bronsted-Lowry acid has given up its proton. Okay? So I'm going to write up a chemical reaction here. Okay, and I want to name the acid and the base, the regular acid and the base, and then I want to see if you can name the conjugate acid. Okay, so does anyone have a clue in our reactant side which is the acid and which is the base? Raise your hand if you think you know. Yeah.
The base is water.
Okay, good. Base is water and hydrofluoric acid is the acid. How do we know that? We already know the name of hydrofluoric acid, so that's a pretty good clue, right? And we also know that this one has a proton that it's going to be really willing to give up, right? If you think about fluorine, it wants to have that -1 charge, right? It doesn't want hydrogen attached to it. It wants that -1. So it's going to give up that hydrogen really, really readily, okay? So here's our acid and here's our base. So knowing what we know about the definition of a conjugate acid, what would be our conjugate base? What would be our conjugate base? Okay, they're always on the other side of the reaction arrow. The conjugate base. So after our acid gives up its proton, right, hydrogen goes away, what's left? A fluorine -1. So this means this is our conjugate base. Okay, it's a conjugate base. Okay, so in our last little section when we were labeling acid and bases on both sides, realistically we weren't labeling those 100% correct, right? This is the conjugate base, so that when the reaction goes the backwards, now we're going to have a conjugate acid and a conjugate base. Okay, so that's just kind of something to think about. So our conjugate base. Any questions about what that term means? It's what's left over after the acid gives up that proton. Okay, and it's going to always be on the other side of our reaction. Okay, so now that means a conjugate acid. What do you think that's probably going to mean?
Only gets added over.
What gets added over?
acceptor?
Yeah. What remains after... Actually, I don't want to say what remains. What is formed? I'll say what is formed. After a Bronsted-Lowry base accepts a proton. So in that same equation, right, we already labeled this the acid and the base. We labeled this the conjugate base. Okay, let's look at our base here. After it accepts a proton, what would it look like? H3O plus. So that means this must be our conjugate acid. Okay, so conjugate base and conjugate acid now could, again, react and go back the other way, right? That automatically tells us that on this side, here's our acid, and on this side, here's our base, right? So labeling it that conjugate acid, conjugate base helps you determine how it's going to work to go backward the other way, okay, or a reverse reaction. Does that make sense? Kind of. Okay, sometimes they're labeled as what we call conjugate acid and base pairs. Okay, they're labeled as pairs. So the way that we label them as pairs, let's say our first pair has to contain its acid and its conjugate base. So our first pair would be made of hydrofluoric acid and fluoride, right? That's our acid-base pair number one. Because here's the acid and here's the conjugate base that forms from it. Okay, so that would be pair, oops, can't spell pair, pair number one. And then water is our base. Where's its conjugate acid? H3O plus. That would be pair 2. Okay, I know I'm just writing over each other all the time, but okay, so when we talk about conjugate acid and base pairs, we're looking for the original acid and original base and what conjugate forms from that. Okay? Now we're going to determine the strength of the conjugate acids and conjugate bases. Right? We know the strength of original acids and bases. How do we determine the strength of a conjugate acid or a conjugate base? Okay, and it's kind of a sliding scale type of system. Okay, so the stronger the acid, that means a weaker, oops, man, I cannot spell today. That means weaker conjugate base. Okay, so if we have a really, really strong acid, let's say, for example, HCl, right? Is that one of our 6 strong acids? Yeah, it's one of our strong acids. So what does it want to do, or what does it do really readily in water? What's it do? Dissociates, good, or ionizes, right? It gets rid of that hydrogen atom, okay, or that proton. It's going to do that 100% of the time. It gets rid of that proton. So that means its conjugate base would be Cl minus. Okay, so we're left with a proton over here that's gone somewhere else, and we're left with the conjugate base of Cl minus. Okay, so how well do you think Cl minus is going to do picking up a proton? Do you think it's going to be very willing to do that or very easily to do that? No, right? It wanted to get rid of that hydrogen so bad. That's what made it a strong acid. That means it's going to be really unlikely to attract a proton and retain a proton. Okay? So strong acids make really bad conjugate bases because they don't want to pick up that proton. Okay? They don't want to do it, right? They want to stay separate. They want to dissociate. They want to ionize. Okay? So really strong acids make really weak conjugate bases. They're not going to be able to attract a proton and retain it to become now a base. Okay? Okay. This goes vice versa as well. So that means the stronger the base. What about the weaker? What about the conjugate acid? The weaker the conjugate acid. Okay, strong base, weak conjugate acid. Okay, and it just works like a sliding scale in between. So if we're like a semi-strong base, that means we're going to have a semi-weak conjugate acid. If we're a really weak acid, we're going to be a really strong conjugate base. Okay, so it just is a sliding scale between those two within that pair. Okay, does that make sense? So if one is really average, we've got an average acid, means we're going to have a really average conjugate base. Okay, so we're somewhere in between that. Okay, I want you to turn to your book. Okay, so go ahead and get out your textbook. And I want you to turn to page 484. 484. This is going to explain that kind of definition or the strength of conjugate acid-base pairs a little bit probably more articulately than I can. Okay? So on page 484, starting at the paragraph 2 where it says this observation, blah, 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 blah. Okay, page 484. I want you to read all the way through that page and onto the next page through that paragraph. Okay, because I think that explains strength of conjugate acid-base pairs better than I can. Okay, so go ahead and read that. Okay, and this is called an amphoteric compound. Amphoteric compounds. Okay, I don't know if any of you got to read that far, but amphoteric was the next little section. And what an amphoteric compound means is that it can act as either an acid or a base. Oops. Okay, what's the biggest example of an amphoteric molecule that we know? Water. Okay, water is our big one, amphoteric. It can act as either an acid or a base. In most of the reactions we've looked at so far, what has it acted as? The base, most of the time. Okay? But if you turn to page 486, just turn one page there, you see a reaction with ammonia. Okay, ammonia plus water leads us to ammonium and OH minus. Okay, so that is, in this case, acting as an acid. Okay, it's giving up that proton. It's unlikely that water is going to act as an acid. Okay, because look how weak of an acid is on page 485. It's really, really weak. Right? If you look at water as an acid, it's like second to the last. Okay, it's really weak acid. So it doesn't act as an acid very often. Most of the time it's going to act as a base. But if it's paired with ammonia, which is an even weaker acid, that means it's going to act as an acid. Okay, does that make sense? Water? Yes, do you see the table on page 485? Water is the third to weakest acid. Okay, so that means it's usually going to be an acid because it's really weak. But in this case, it was with ammonia, which is an even weaker acid. So that means ammonia is going to act as the base and water is going to act as the acid. Okay.
Wait, but ammonia